In this video, we'll look at quantum theory and matter wave properties. And this brings us to our next physicist, Louis de Broglie. So de Broglie thought about, well, if photons are kind of like little packets, little particles of energy, act like a particle, like something with mass, but they also act like a wave. So if a photon can be both a solid particle and a wave, why can't everything else? Why can't an electron moving around the nucleus be a particle, an electron, or a wave, act like a wave moving around the nucleus? Why can't an atom, which is a particle, act like a wave? If a photon can, why can't an atom? What's stopping it? It can be extended further where if you have a solid object, if it moves fast enough, can't it have a wavelength? Can't it act like a wave at some point? So de Broglie thought about this. If photons can both be particles and waves, why can't other things? And so it came up with the wavelength of an electron or any other particle purely depends on its mass and its velocity, as long as we obey Planck's constant. So he came up with our wavelength of anything equals Planck's constant divided by the mass times its velocity, or the momentum of that object. So as long as the object has momentum, in theory, it can have a wavelength. Now, we may not be able to perceive these wavelengths, but in theory, it can have a wavelength. So if we look at this and look at the electron moving around the atom as a wave. So if we remember, our Bohr model had our electron for our hydrogen atom moving around in concentric circles. So it moved around in circles around the atom. If we took that and took the idea that it was actually moving as a wave, or kind of a wave motion moving around the atom, it can look like something like this. All right, first n equals 1, n equals 2, 3, 4, and you can kind of see the wave pattern of the electron moving around, where it's kind of going up and down, almost like a little roller coaster. If we straighten it out, we can have n equals 1 completes one wave pattern, n equals 2 completes two wave patterns. And you can see n equals 3 completes 3, n equals 4 completes 4. So this is how we can have our allowed states. We have to complete a full wave pattern or a full wave to have a allowed state. Anything that stops in the middle of the wave and doesn't complete it, that's not allowed. Okay, so now let's practice this idea. What is the wavelength of an electron that moves at a speed of 5.97 times 10 to the 6 meters per second? And the mass of the electron is 9.0194 times 10 to the negative 31st kilograms. So if we use de Broglie's equation, that says that our wavelength equals Planck's constant divided by its mass times velocity. So here I'm given a mass, here I'm given its velocity. And I know Planck's constant, it's a constant. So I have my lambda equals 6.626 times 10 to the negative 34th joules times seconds, divided by that mass of 9.0194 times 10 to the negative 31st kilograms, times its velocity, 5.97 times 10 to the 6 meters over seconds. So if we look at this, you might be thinking to yourself, eek, none of the units cancel. I know wavelength has to be in meters, and I have a meters here, but it's on the bottom. I need to get a meters on the top, and I need to cancel out a joule, a second, another second, and a kilogram. There's a way to do that. So a joule equals a kilogram times meters squared over seconds squared. So now I can cancel out all my units and get just meters on the top. Yay! So now once I take all this and I punch into my calculator, I end up with 1.22 times 10 to the negative 10th meters. Or you can think of it as 0.122 nanometers. Now, if we look at where this falls in the electromagnetic spectrum, this actually falls into the X-ray region. So you can almost think an electron moving at 5.97 times 10 to the 6 meters per second is the same thing as an X-ray. So X-rays could just be electrons moving really, really fast. Or electrons moving really, really fast become X-rays, depending on if we want to perceive them as a particle or as a wavelength. And we can even do this calculation and figure out the wavelength of you moving around in a car or on an airplane or the Earth moving around the sun. We can calculate a wavelength for everything. So now that we know particles can also be wavelengths, particles and wavelengths can exist at the same time. So now that we know particles can also be wavelengths, let's think more about this and look at another scientist, Heisenberg, and Heisenberg's uncertainty principle. So what Heisenberg showed was the more we know about how fast something goes, its momentum, the less we know about its location. Or you can also think about it, the more we know about its location, the less we know about its momentum. So if we know the exact location of an electron, we have no clue how fast it's going. If we know how fast the electron's going, we have no clue where it is. Kind of trippy, right? But you all have kind of experienced this in your everyday lives. Just never realized it. So if you think about that ball dropping, the ball dropping from the 6th floor down to the 1st floor. So you dropped a ball, or say you dropped a watermelon off the top of the building. Please don't do that in real life. So let's think about if you have a ball and you're on that 6th floor and you drop it down to the 1st floor. When you let go of that ball, you can watch it drop. You can watch how fast it's going. But every time you blink, the ball's in a different position, right? The ball never stays still. It's always moving and it's in a different position. And if you watch how fast it goes, you never know its exact location during that descent down. But if you know exactly where it is, you look at it, you don't know how fast it is. Or if you take a picture of that ball dropping, if you take a picture, you know the exact location of that ball. But you don't know how fast it was going when you took that picture. That picture doesn't tell you how fast it went at all. It just tells you exactly where it is. Or if you watch it unblinking, you can see how fast it goes down. But you never know the exact position at any given instant because it's always moving or changing. And so Heisenberg took this idea of the more we know about its position, the picture you took, the less we know about how fast it goes, so its momentum. Or the more we know about its momentum, watching the ball drop, the less we know about exactly where it is at any given instant. And so this happens with electrons. And in many cases, the uncertainty that we know about electrons, that we know about its whereabouts, is actually greater than the atom itself. The size of the uncertainty, because we know the speed, so we don't know its location, the size of that questionable location is actually bigger than an atom, which means we really have no clue where an electron is in an atom at any given point. We have absolutely no clue exactly where an electron is at any given instant. We just know they're there. And so this takes us into our final scientist for our quantum mechanics here. This takes us into Schrodinger. And this is the same Schrodinger that came up with the whole cat experiment. So what Schrodinger did was he came up with a wave function to try and figure out and explain where the location of the electron will most likely be. So we're looking at probability. How likely will the electron be at any given area of the atom? And so he used de Broglie's idea about the wave property of electrons. He used its electron momentum and its energy using Planck's relationship to come up with an equation. This is what the Schrodinger wave equation looks like. And when you solve it, you can start to figure out where the electron will most likely be in an atom. Don't worry, we're not going to solve this. We're not touching this equation in this class. But this is how you would figure it out. And Schrodinger is the one that came up with this idea and combined all these other scientists' ideas and theories together to come up with a wave equation. And doing that, we end up with a probability map. So if we look at our blue one here, all those dots are the Schrodinger equation solved. So put in a computer, it'll solve it for you. But what that means is within this area, this is the most likely area we'll find the electron. And you can see there's more and more spots the closer we get to the nucleus. And so if we look at it and we draw orbitals around it, hey, look, we're more likely to be in an n equals 1 or n equals 2 orbital. Further out you get, the less orbitals you get. And then since life is not 2D, life is actually 3D, all these dots are actually connected in 3D space. And so if we put in 3D, our circle becomes a sphere. So it's more of a sphere of where the electron can be than an orbit. It's more of a sphere than a circle. And so when we decide where that electron's going to be, where we make our cutoff, generally we make our cutoff, there's about 90% chance the electron will be inside the black circle. And you can see it goes higher the closer you get. So that black circle represents the probability that 90% of the electron, 90% of the time the electron will be inside the circle. 10% it'll be outside. And so when we do this and we create the sphere around where that circle is, that's where we get what we call an orbital. And the orbital is where the electron resides, kind of like an orbit. So we keep Bohr's idea where it came in orbits, but now we call it orbitals. Instead of thinking of concentric circles outward like a solar system, think of the orbitals and where the electron can reside more like a jawbreaker and the different layers of a jawbreaker. And then that can give you a better idea about how these orbitals might exist. Think of it more like a jawbreaker, where you have your outer color. Once you finish all that, now you have a yellow. Finish all that, it might be pink and a blue. And then if you cut the jawbreaker in half, that's where you can see the lines where it kind of looks like an orbit, where it kind of looks like a circle. So you can think Bohr's model, where he said there are orbits, he might have just had that jawbreaker cut in half. But the real idea is the electrons move around in a sphere. They move around on a sphere around the atom. And then now one last point, when we think about that jawbreaker. Yeah, say with our jawbreaker, we have our different lines here, our different orbitals. And remember, the electron is only allowed to go between certain ones. So it has to go either from the top to the bottom to the next one, or from the top down there. So what about that empty space? What about this little space in the middle? Why can't it stop there? And so for something like that, we have to think about what we call nodes. A node is the place where electrons not allowed. So that would be like our n equals 1/2. Electron can't stop halfway. Schrodinger's equation says that the electron is not allowed to stop that halfway. So the electron has to be on kind of the edge of each of those circles, each of those spheres. And so he also figured out that our orbitals possess n-1 nodes. So orbitals have n-1 nodes. What does that mean? So that means if we're looking at an electron in the n equals 4 level. So if my electron is in n equals 4, that means it's going to have 4-1 nodes, or 3 nodes. So there's kind of 3 positions in that 3D sphere, or 3 distances in that 3D sphere that the electron's not allowed to go to. And so now we've learned a little bit about the wave matter properties using de Broglie, a little bit about uncertainty of where the electrons are actually located with Heisenberg, and then using Schrodinger's equation and Schrodinger, we can start to figure out where the electron most likely resides, since we don't know its exact location. We start to figure out probability shells or probability maps of where the electrons can be. And then in our next video, we'll look a lot closer at these orbitals and actually discuss more about these probability maps and how they look different for different n levels.